Okay, let's work through this sample test. First of all, it says graph the data. So I'm going to try to make a nice large graph on this. Pull out a ruler. Find one. Must be one here somewhere. There we go. I'll make a x-axis or a y-axis here. X-axis down here, or independent variable down here somewhere. And I say you have to label it. So this is the height, the drop height. As the independent variable. And that's measured in centimeters. So I got labeled and units. This way I need to label it, and this is the bounce height. This happens to be also in centimeters. And now I have to figure out a scale, and I got to get to 300. So 10, 20, 40, 60, 80. I can make that 100. 20, 40, 60, 80, 200. 20, 40, 60, 80. Oops. 0. 20, 40, 60, 80, 100. 20, 40, 60, 80, 200. 20, 40, 60, 80, 300. That fits on there, okay? And the other way, I have to get to 230. I can do the same scaling. 20, 40, 60, 80, 100. 20, 40, 60, 80, 200. 20, 40, 60, 80, 300. You don't have to put numbers on every line, just enough so we can follow where and keep track of where you're at. And I'm using a significant portion of the graph. I want it to be large enough that it's using major part of it. I wouldn't do 100, 200, 300 on the x's because that's way too small a graph. 10, 8. 20, 15. No, that's 20, so 15. 8 is down here. Whoops. I'm already messing up a little bit. Oh, there we go. That's 20, so 8 is less than half, and 20 is 15, and 30 is 25. So I got this one, and this one, not that one, and not that one. And then I have 50, 37, 50, 20, 40, 37 is almost on the line. 100, 82. There's 82 barely above it. And 200, 175. 100, 20, 40, 60, 80, 75. It's about there, 3/4 of the way up that square. And 300 to 20, 30. So determine a slope of a line. So I'm going to pick a line a little bit above that one, below that one, and hits these points here pretty well. So something like that. This is going to depend on so you're going to draw a line, and then I'm going to try to read your line and what you get for the slope. So the slope, it looks like it goes pretty close to this point, which is 180 roughly, 182 roughly. And it looks like it hits this one right on, which is 220, or here even I could go out to there, hits that one nicely. I'll go here, I get 220. and a height of 180. Again, which points you pick will make a difference in this, but your answer should be close to what I get here. So it went up roughly 100. It went up 98. The rise is 98 centimeters. Over the run, it went from 100 to 220. That's 120. Centimeters cancel. So I get a slope that's 98 over 120, or you could multiply that, or divide that. 98 divided by 120, and I get 80, basically 80.82. And the interpretation of this means that for every 1 centimeter more, it bounces 8.8 centimeters, 0.82 centimeters back. For every, because this is over 1, or you could write this as 82 hundredths. For every 100 centimeters higher I drop it from, it bounces 82 centimeters higher. Or you could say the bounce is 82% of how high you drop it from. That's another interpretation. There's several ways you could write the interpretation. I'm hoping you pick one that makes the most sense to you. Now the y-intercept on this one, just looking at the graph, looks like it's 0. And its meaning is if I drop it from a height of 0, I get 0 bounce. Now, you may have gotten something a little off from 0. You might have said it was 1 or minus 3 or minus 3 or plus 3 or something down here. If you read it a little differently or made your line a little differently, it still is when you drop it from a height of 0, because the drop height would be 0, and it's telling you a bounce height that it should be. And if you had something besides 0, it's saying it's bouncing negative or bouncing positive. A little bit of nonsense. In this case, 0 makes sense. If you drop it from 0 height, it should bounce 0 height. Okay? So that's the idea of this part. Now the second part, part 2, you're supposed to look at this and use technology. Now I'll do the regression model on the calculator, but you can also do it on Desmos. So just in case you're using a calculator, here's how you would do it. Let's get the data close. So we push Stat, Edit by pressing Enter, and then I go into my X list, and I could just type over these, or I can go up on list 1's name, push Clear, and then come down, and now I can put in there 10, 20, 30, 50, 100, 200, and 300. List 2, I'm just going to type over on these. 8, 15, 25, 37. Oop, I missed something here. 30 is 25, 37, 82, 175, and 230. Excuse me. So now I can go Stat, calculate a line linear regression for this data. My X's are in list 1, my Y's are in list 2. The lists are in the blue above the numbers here. And you can change these if you have them in different lists. And I can calculate it. And I get a line with a slope of 0.7951. 0.7951. Slightly different than my estimate. I had 0.82 on my graph here. It chose a little less slope. Maybe based on there's more points here that might have pointed it for a little less slope. Okay? So the technology learned by, it says y equals 0.7952 times the x. Notice it says a times x, and that's the a that goes there, plus the y-intercept of 1.05, 05922, so I'm rounding it off. So it picked a height a little bit more than 0. So it's saying, this model says if I drop it from 0, it's going to bounce 1 centimeter. Doesn't make sense, but that's what this model predicts. Now, how good does this line fit? And that's the r squared or the r. And they're both on this. The data is a pretty good line, and they're both saying 0.99, which is really close to 1. It's not 1, but it's 0.99, so great fit of a line to the data. Okay? The line makes a pretty good fit. Okay. Now we just have to answer these. So now you have to know where to look for slope. Slope is times the x. It's negative 2/3, so it's going down 2 for 3, which means it's decreasing. This one, it's 3x, a plus 3x, so it's going up 3 for 1, so that's increasing. This one has no x, and if you graph y equals -5, it stays the same height all the time. It's constant. It's not going up or down. Now write the equation through these. Well, we got to figure out the slope. So the change in y, it went from 3 to 5, so it went plus 2. That's the rise. 3 to 5 went up 2. You can graph it and see that if you want. And the x went from 2 to -3. That went back 5. So there's the slope. And it's y, or f of x, equals the slope times x plus a y-intercept. So let's find the y-intercept, some number that we have to add to make this work out. So if I put 2 there, I get 2/5, -2/5 times 2 plus something that I'm trying to figure out has to come out to be 3. If x is 2, the function f of x or y has to come out to be 3. So this multiplied, so we get 3 equals, this is 2 over 1. We multiply the numerators. We get -4 over 1 times 5, 5 plus b. So I add 4/5 to both sides, and I get 3 4/5 is b. So now I have to write the function. So I want to write function f of x that has this slope. You can write that as, and you can type in -2 divided by 5, and you'll get -0.4 if you want to write it that way. But it's got to have an x plus the y-intercept, which we figured out was 3 4/5 or 3.8. And there's the equation of the line through those points. Now we pretty much have to do it again. Write a linear model for the population from 1950. If t is 0 in 1950, so this is 40 years later, so this is t is 40. So we have 0, 0 is 7500 population. And year 40, the population dropped to 2,300. So this is a decreasing model. This is an estimate for what happened to, say, Clayholme or Roslyn after the coal mine shut down. The population went way down. It's now going back up, but it went way down for a long time. Up through the 80s and 90s, it was down. All right, so what was the increase? Well, it decreased by 5,200 people. So the change in the y is minus 5,200. It went down 5,200 people over 40 years. So I can figure out what that is in decimal if you want. Let's see, 5,200 divided by 40, that is 130 people per year. So the model would be the population as a function of time, number of years, is minus 130 times the number of years after 1950 plus the y-intercept. Well, that's going to be, since I made 0 be 1950, and the population is 7,500, that would be 7,500. So that if I put 0 in for t, I get 0 times this plus that should give me 5,000, or 7,500. So this is the model. So what is it in 2005? Well, that's 55 years after times 0. So I'm going to put 55 into here, and it'll tell me how many times to subtract 130 from 7,500. So negative 130 times 55 years later, losing that many people, starting with 7,500, and we'd end up with 350. That's assuming that things stayed the same as they did from 1950 to 1999 and continued on. However, that's not what's happening in those towns. It's now turned around and it's growing again. So this model, linear model, isn't correct, but it is something we can use to predict based on those 40 years. Okay?